for this video, which comprises a ripple carry adder, a multiplier, and a mux. The inputs are two 4-bit buses that correspond to the outputs of the register file muxes that choose which registers we're going to be using from the register file for our calculations in the ALU. So that's A and B. We can take a look inside the ripple carry adder, which is just a bunch of full adders calculating each bit of the sum, as well as the carry out bits. So it takes the two 4-bit register out, 4 bits of the registers basically, and produces a possible 5-bit output depending on if we have a carry out on the output or not. The full adders are made up of half adders and an OR gate, and the half adders are made up of an XOR and an and all that inner circuitry was developed from logic equations from truth tables. So I won't go into too much details about that. So that's the ripple carry adder. Takes two 4-bit values, produces a possible 5-bit value as the sum of those two inputs. The multiplier is an array multiplier, the most complicated circuit that we had to make. That's a combination of half adders, full adders, and AND gates in a specific configuration that then produces the product of two 4-bit inputs, which are again those registers that we chose. And what's unique about this is that it has a possible 8-bit output, just based on carry outs from the multiplication process, essentially. So that's what the array multiplier looks like. And then, so those two outputs get fed into a mux, which basically chooses using instruction bit 7 whether we want to take the sum or the product of the two inputs and use that as the output of our ALU. And the mux 2 to 1 is actually just a bunch of 1-bit muxes in parallel, because the inputs of the mux that we use in the ALU are actually buses, so we need multiple muxes for each bit. So input 0 on each mux corresponds to the output of the ripple carry adder, and the 1 input on the mux corresponds to the product from the multiplier. Select bit again is that instruction bit 7 that tells us what kind of operation we want from the ALU. What you'll notice is that the inputs are actually of different length. The add is at most 5 bits and the multiply is at most 8 bits. So we actually need to do for those upper 3 muxes, where we basically run out of bits in the add, we just ground them so that the upper bits of the add input are zeros, so it doesn't actually affect the value. And then we mux that with the multiplier bits so that we get the proper output on the mux output, which needs to be 8 bits long, as you can see here. So yeah, we basically calculate the different operations that we need, and then we choose the correct one using the mux. For this component, I would use a transient simulation where I use that trick you showed us with the varying periods of the bits on the inputs to generate all possible values for A, all possible values for B, where you basically half the frequency for each successive bit, so bit 0 being the fastest, bit 3 being the slowest, having the frequency each time. Then I would also, so I would check these output terminals to make sure that the sum or product is correct based on the logic here. And then I would also vary instruction 7 so that we're looking at both the add input and the multiply input to the mux to produce the correct ALU output.